So when we're moving up and down like this, then we say that the particles are moving in a direction transverse to the wave's motion. That means that we can call these transverse waves. So some media, such as gases, for example, can't actually transmit mechanical transverse waves because the gas particles are simply not connected to each other. We can't get a gas particle moving up or down, getting the gas particle next to it to also move up or down. For a slinky, we are able to do this. If one part of the slinky moves up, then it will pull the next part of the slinky up, and so the wave will propagate. Electromagnetic waves happen to be a form of transverse wave, because if we shake an electron in one direction, then the wave will propagate perpendicular to the direction that we're shaking the electron. So when a medium vibrates parallel to the wave's motion, then we say that it's a longitudinal wave. And so we can see that in the example of the slinky. The parts of the slinky carrying the wave are vibrating in the same direction as the wave is traveling. And we can see that that will allow the wave to propagate through the slinky. So sound waves are a type of longitudinal wave because for sound waves, the air particles which are carrying the wave vibrate in the same direction that the sound wave is traveling, right? So sound is able to propagate through solids or liquids or gases. If we have a sound wave trying to propagate through a gas, then the gas will vibrate in one direction, and that means that it will collide with gas particles next to it. And so in that way, the wave can propagate through the gas. Compare the motion of particles in a transverse wave to the motion of particles in a longitudinal wave. Now, can you remember the difference between these two? In a transverse wave, the particles will vibrate in a transverse direction to the wave's motion, which means perpendicular. And for a longitudinal wave, they'll vibrate in a direction that is longitudinal to the wave's motion, which means in the same direction. So in transverse waves, the medium oscillates perpendicular, and in longitudinal waves, the medium oscillates parallel to the direction of energy transfer. It turns out that there are one or two other forms of wave, such as toroidal waves. If we think about a spring that we twist up, when we let go of it, it'll twist back into its original shape and then keep going. After it's done that, it'll twist back again. And so we'll get a clockwise twisting and then a counterclockwise twisting, and that will repeat. So what we have there is a toroidal wave, which is traveling not across, but in a circular direction. Classify the following waves as transverse or longitudinal. A ripple in a pool of oil. Now in this case, we have a mechanical wave that's causing the oil particles to move up and down and to affect other oil particles with surface tension. So if an oil particle moves up and down and then affects the next one with surface tension, then when the first oil particle goes up, the second oil particle, pulled up by surface tension, will come up next to it, and that'll pull up the next oil particle, and so on. And so we get the wave propagating. And if the oil particles are moving up and down, and the wave's propagating in that direction, then they're vibrating perpendicular to the wave's motion. So we have a transverse wave. How about a sound wave traveling underwater? Now, if we look at ripples on the top of the water, then they'll be using surface tension. But underwater, we can have sound waves, which travel in the same way that they do as in air. That is, we get a particle vibrating back and forth and bumping into its neighbors and causing them to vibrate back and forth as well. And then they'll bump into their neighbors and so on, and the wave will propagate through the water. So in this direction, if the wave's moving in that direction, and then the particles will have to be vibrating in the same direction as well. And that means that they'll bump into each other, right? So we have a longitudinal wave. How about a radio wave broadcast from a satellite? Now this one's a bit harder, because in this case we don't have any particles vibrating. There aren't any particles in space where satellites are, and so we have to travel without particles. In this case, we don't have particles vibrating, but we do have electric fields forming in a direction that's either longitudinal or perpendicular to the wave's motion. Can you remember which? That's right, it's transverse. So in an electromagnetic wave, like a radio wave, the electric field that causes the wave to propagate is transverse to the wave's motion, that is, perpendicular.